This is session from here. Okay. So earthquakes and tectonics. Yeah. Good afternoon. Welcome and welcome back. I think we should get started. Welcome to the Earthquake and Tectonics, the third session. In the interest of time, we'll get started. The first speaker here is Brian Rambo. He'll talk about surface displacement throughout the earthquake cycle over Haiti's southern peninsula.
Do you hear me well? Yes, cool. So my name is Rambo Brian. I'm a third-year PhD student at the École Normale Supérieure, and today I'll talk with you about the surface displacement throughout the earthquake cycle over Haiti's southern peninsula. So we are located in the Caribbean, where the North American plate subducted beneath the Caribbean plate at a rate of 2 centimeters per year. And actually, you can see that it is a quite active area with a lot of earthquakes. And we are going from a frontal subduction in the Lesser Antilles to almost a collision when we reach Hispaniola Island, which is there, with mainly strike-slip faults. So if we zoom in, this is the context of the Hispaniola Island, which is composed of two countries, Haiti and the Dominican Republic. And as you can see with the white stars, the past seismicity and tells us that this is an active area that delineates two major strike-slip fault systems. In the north of the island, you have the septentrional fault, which has a fault slip rate of 9 plus or minus 3 millimeters per year. And when you go down in the south, near Haiti, in the southern peninsula, you have the EPG fault, which has a rate of 7 plus or minus 2 millimeters per year from paleoseismology and models of blocks. So the EPG fault is actually quite well known for the the deadly and famous earthquake of 2010 and 2021. And you have also plotted there the GNSS velocity in the North American reference frame. And you can see that from the north of the island to the south, there is a huge velocity gradient, meaning that strain is actually heavily accommodated through the entire island through multiple faults. So we're gonna ask an easy question, which is not that easy to answer. There is all strain is partitioned along this transpressive system. And as we have two earthquakes and geodetic data that covers one of the earthquakes, we can go through multiple phases of the earthquake cycle. So here is the view. We have 6 tracks covering the island. So we're gonna process them all and stop at the square time for the interseismic period for the track 4 and track 142. And for the post-seismic, we're gonna start right after the earthquake. So a bit of processing. I won't go too much into detail because this is not the point of the presentation, and this is well-known techniques. So we start with Sentinel-1 ABSR images, and we do persistent scatter interferometry and also distributed scatter interferometry. First, for the persistent scatter interferometry, we process the SAR images with ICE2, and then we compute single-loop complex images in full resolution that will feed into stamps and to get a time series of PS, and then correct that time series with the train atmospheric toolbox. This will be it for the interseismic analysis. And on the other side, we will multi-loop the interferogram and wrap them. We'll use that for the co-seismic analysis and then correct the interferogram with PIAPS and ERA5 atmospheric models, and then feed that into the Kalman filter time series analysis to extract post-seismic displacement. So directly to the results, you have there plotted the PS velocities. On the top, you have the descending track, and on the bottom, you have the ascending track. And when you look at that, you can see on the descending track, actually, that there is a velocity gradient through the septentrional fault, which is there. So we have a velocity gradient on this fault, but we also have the same thing on the EPG fault, which is on the southern peninsula. And actually what you can see is that the velocity gradient is opposed in both line of sight, which actually means that strain is accommodated there, and also that given the line of sight geometries, that this is mostly left lateral. So we are happy in a sense that it matches the transpressive context of the area. So we also have the GNSS data in the ITRF reference frame that we projected to the ascending and descending line of sight. And we plotted one against another. And you can see that our velocities, our INSAR velocities matches quite well our GNSS velocities plotted in the ascending and descending line of sight, projected, sorry. We then reference the INSAR velocities to the GNSS velocities. So you have there an average profile along the septentrional fault, and what you can see, you have in red the ascending INSAR velocities, and in blue the descending velocities, and we reference each profile across the distance from -20 to -40, and you can see that at the fault position it diverged, meaning that there is an opposite gradient of velocities on both line of sight. And when we plot then the GNSS ascending velocities projected in the ascending line of sight, and the GNSS projected in the descending line of sight, you see that it matches quite well our INSAR data. And now, if we take a look at the EPG fault, strike slip, we can see that we can fit the displacement that we observe in the ascending and descending line of sight very well with a simple strike slip screw dislocation. So this is a bit intriguing because we are in a transpressive system and we matches quite well the strike slip. We matches quite well, so is the velocities with strike slip only dislocation. So there might be things in the INSAR that maybe we cannot see the north-south convergence. So we extract EPG fault looking depth and the EPG fault slip rates. This is still work in progress, but this is actually good stuff in our opinion. So partial conclusions about the interseismic period. We have an interseismic PS study that agrees well with the GNSS campaign data. We model with a strike slip only dislocation the GNSS, the ascending and descending velocities. So what about the convergence across the transpressive system? Maybe the ascending and descending line of sight might be insensitive to the north-south convergence, which is probably the case. So we're gonna need to take the 3D GNSS in the future. So in our estimated rates also, we are in agreement with what paleoseismology and model of blocks says. So now that we have seen that in the interseismic period, there is a strain accumulation on faults, we're gonna go through the seismic period and see if the release matches the transpressive system in a sense that what is released during the seismic period. So you have there the GNSS displacement, seismic displacement on the top left corner, and on the bottom line you have the descending Sentinel-1 and descending ILOS-2 data, and you see that the pattern matches quite well, while it is completely opposed in the ILOS-2 ascending track on the top right corner. So actually, what we can extract from that rapidly is that, this area has been going up because we can see that it is red in both line of sight, and this area, we have an opposed pattern in displacement, so it means that it is mainly strike slip motion. So we have a dual release during the co-seismic with a strike slip and deep slip. So a rapid model of the co-seismic displacement that you can see there, and you can see that we have two faults that matches well the displacement that we can observe at the surface. So we have the rupture of two faults, but not the EPG fault, which is quite intriguing because it is known to be the fault that have been ruptured in the past years. And also we have an overall moment of 1/3 of deep slip and 2/3 of strike slip, which actually matches quite well the interseismic velocities that are being accommodated there. So we can see the partitioning. So this is a co-seismic model from the published study, and actually we have the same story. It ruptures first a secondary thrust and then runs parallel to the EPG fault with only strike slip motion, as you can see on there. First thrust and then strike slip motion. And it also ruptures another fault than the EPG fault, as highlighted in red on the bottom left. So partial conclusion about the co-seismic period is that we have rupture of secondary thrust fault rather than the EPG fault, and we have also comparable faulting event in 2010 and 2021. Actually, we see the partitioning of the transpressive system during the co-seismic release. Now, what can we see in the post-seismic period, which is, in my opinion, the most interesting part? So, in 2022, Yin and collaborators, as I think Yin is there, Zoe, sorry, and they observed co-seismic fractures in the wake of the 2021 earthquake. So they also identify some post-seismic slip on secondary faults, and these fractures actually hold right lateral motion and left lateral motion. So this is a bit weird because we are in a transpressive context, which is mainly left lateral. To see right lateral motion is something that we did not expect. So to match this quite quickly to the Coulomb stress changes associated to our 2021 co-seismic model, what we can see is that for a vertical strike slip east-west fault, you can have the fault in green that are located in the areas of Coulomb stress increase, which matches actually the fault localization. So maybe the co-seismic fractures are linked to the Coulomb stress changes. So actually, we wanted to be sure of what we observed. So we processed Sentinel-1 data right after the earthquake. And we identified in the cumulative line of sight time series the multiple faults that have been activated. Some are matching the one that Yin and collaborators found, and some are new ones. We interpolated ascending and descending time series and project them to EPG fault parallel and vertical displacement. And after that, we draw systematic along strike profile for each fault with fault parallel displacement projected along fault azimuth. This is what we get. We have faults that are moving after, in the wake of the 2021 earthquake. We extracted along strike fault offset displacement on regularly spaced along the fault, and as a function of time that is plotted there on the top. We measure the step across the fault by subtracting the mean values within a given length of the fault trace on each side. And actually, this is not the only one. We have 14 fault segments that are holding left lateral or right lateral motion. We also checked on the raw ascending and descending time series to be sure that what we observe is actually something true. It is the case. And when you look at it in another way, on the, for example, the figure on the top left, you have the the cumulative offset at the maximum creeping location of the fault as a function of time. And you can see that it has a logarithmic decay characteristic of after slip, but that is not on the fault rupture. So secondary faults there are slipping after the 2021 earthquake. So as we see after slip, we link that to rate and straight friction law. Basically, it tells us that the cumulative offset is equal to those parameters up there, and that we can extract A minus B values telling us the fault behavior and fault rheology. And what we get is that all fault segments have a rate strengthening behavior, which is characteristic of faults that are prone to slip aseismically if stress is applied on them. So we had a few questions about what we can see. So we first thought it was a compliant fault zone, but it looks like it's not purely elastic because we have a time dependency. We have a characteristic time for slip, and so we removed that hypothesis. So then we have the logarithmic decay of fault slip, meaning that the fault has a response through time. So we thought about a viscous response, but for a 5-10 week event, the drop of viscosity for such event will be very unlikely. It will mean order of magnitude for a drop of viscosity that is impossible. Sorry. So it's most likely frictional. And now, the most interesting feature is that when we compute the Coulomb and shear stress redistribution, we computed it for each fault orientation, and we see that fault creeping segments are in area of Coulomb stress increase. But when you look at the plot on the right, we have faulting type that depend on the shear stress variation. what I mean is that this part is for left lateral faults, and this part is for right lateral fault slip motion. So depending on the shear stress variations, we have faults that are moving in the sense of the shear stress. So this is a partial conclusion about the seismic period. We have multiple secondary faults activated. We have frictional rate strengthening behavior for all segments, and we have a strong link between the co-seismic stress redistribution and the Coulomb G stress variations. And what we think is that secondary faults here are passive markers responding only to the shear stress variation in Coulomb stress variations. If you are not sure about what I said, we can have a look at what's happening after two earthquakes in 2022, two magnitude 5 earthquake, for which we extracted the displacement in the time series. And we plotted there the earthquake timing in red. And you can see that right after the earthquake, the fault NE1 and NE2 that are there are slipping. So this is something that is happening a few times in the same fault zone. And it matches the Coulomb stress increase areas. Now, if we take a look at the 2010 earthquake, because we have data also for that, but on the ALOS one, we have a small time series of 5 images, and we draw a profile to the red rectangle that you can see on the top left. We see that there is also a fault slip happening there. So, summary and conclusions. We highlighted in this presentation the partitioning of the transpressive deformation that is visible in the GNSS data and in the co-seismic period. We have large ruptures that initiate as thrust and evolve as strike slip fault when they get closer to the EPG fault. The EPG fault is actually locked at depth while presenting a rate strengthening behavior in its shallowest part. And the main result of this presentation is actually that we have a frictional response of multiple secondary faults to the Coulomb stress redistributions, which actually means that we have passive markers reacting to stress. Thank you. Sorry. Thank you for your attention.
Yeah, this is very interesting. It seems to imply that there is simply no stress in the topmost layer of the Earth. It's completely stress-free. Unless you have some kind of a compliant material and you're seeing some kind of a decay constant of a finite width zone, could you really tell if it's on a really sharp boundary? And then can you say anything to which depth it may extend this kind of motion?
Sorry, can you speak a bit louder for the last
Yeah,
part?
so twofold question. Can you rule out that this is not a shear zone with finite thickness? Is it really a sharp fault boundary that is moving? And can you say something about to which depth this secondary fault slip or motion reaches?
Actually, yeah. I will try to answer the question. I think that is something fault slip because actually we saw that from the study of Yin and collaborators in 2013 with values to stake phase gradient that there is no unwrapping in that. So it's most likely pure information. They identify the fault fractures, and if I remember well, they also identify some post-seismic slip on those fractures. I mean, they say that they saw the fault slip. So I think that is a good agreement with what we are seeing there. And yeah, and about the compliant fault zone, actually, the context of this area is a bit weird because we have oceanic crust that is the arc of the southern peninsula, and we have a fault thrust that is just north of the peninsula that is abducting what can be called some other continental crust. So we have some kind of probably weak, very weak fault zone with a lot of stress in that. That can, I would say.
Okay, John.
Thank you very much for that. The EPG fault seems to be not doing anything in your total analysis of the earthquake cycle. I mean, what strong evidence is there that it actually exists as a locked vertical strike slip with a shear zone vertically beneath it?
Okay. Yeah, actually, the field tells us that it is a strike slip fault. I mean, there is features from the field that actually this cannot be something else than a strike slip fault with large earthquake that happened in the past. But yeah, actually, we do not have that much information for now because the political situation there is a bit unstable, and so I wish I could go there too.
but that it persists as a vertical extensive structure.
For the vertical, yeah, some studies from geological mapping tells us that to the east, it's most likely not vertical, but southward dipping. But we do not know what's going on there, unless that we have some aftershocks relocations that seems to align along the vertical structures after the 2021 earthquake. So this is not an answer, but this is some first guess.
Okay, thank you very much.
All right, we should move on. The next speaker is Chi Yu from University of Leeds. She'll be talking about large-scale velocity mapping over Tian Shan Mountains.
Thank you so much. As Sanho said, I'm Jill, a postdoc at the University of Leeds, and today I'm going to present our group's collective effort mapping the large-scale velocities over the Tian Shan Mountains. So here is Tian Shan, which is a reactivated orogenic belt at the northern front of the Alpine Himalayan belt. And these are the velocity vectors. As a whole, the Tian Shan Plateau is absorbing about half of the convergence between India and Eurasia. If we zoom in, we can see the velocity vectors fan out as it shortens. How this deformation is being accommodated through the fault structures here is not 100% clear, and which faults are more active than others, and how fast is Tian Shan rising, or is it? So these are the 3D vertical velocities being compiled from different studies. The brown points are showing uplift, whereas the green points are showing subsidence. So we are seeing really a mixture of both. From our past experience, we know that the high resolution INSAR velocities have really helped us identify the sources of the potential vertical motions. And we would like to do the same for Tian Shan. So this is our INSAR coverage. We processed 90 LIX frames of Sentinel-1 data acquired from 2014 to present. It's a really challenging area, as you can see from this average coherence map. And apart from the Kazakh platform, stable Eurasia in the north, as well as the fold and thrust belt in the south, we almost have low coherence everywhere. And because it's a hard place to do, we gave it our best shot. We came up with a Tian Shan strategy, which is LIXAR processing chain with a twist. The differences are we used the Copernicus 30-meter DEM to do the topographic corrections and the geocoding better. We chose a primary epoch somewhere in the middle of the long time series to facilitate co-registration. We process interferograms to 50-meter resolution to give us a better chance of preserving more pixels in the end. And for the network, we make interferograms with every 5 consecutive links, as well as 3, 6, 9, and 12 months long temporal baseline interferograms. So I have a great redundancy to start with. For the time series analysis, again, we are using the LIXBus system and with the twist. So apart from picking out interferograms with missing burst, we also automatically detect interferograms with co-registration errors and implemented a way to automatically correct unwrapping mistakes rather than mask out unwrapping mistakes from our interferograms based on the residues derived from time series analysis. We use all interferograms processed to do this first iteration of time series of time series inversion and unwrapping mistake correction, so that we have more robust residues to help us with the unwrapping mistake correction. And once we are happy with the interferograms, we drop all the 6-day, 12-day interferograms to mitigate potential phase biases problems. So this is an example of our final data set. We are losing a lot of the winter epochs, as understandably, because there's the snow cover in the winter. But in the end, we have strongly connected networks with no gap in between and no loop error, and with residue RMS below 1.5 millimeters. So the effort is paying off. If we mosaic the frames along track by a constant between them, we can get those long, smooth line-of-sight velocities. And this is what they look like in total as a whole. To the first order, we can see this ramp, a long-range ramp across all tracks. And then that is because of the plate motion as seen in the line of sight due to the changing instance angle. And this we can forward model and correct using an approach demonstrated by Stephenson et al. 2022. These are the plate motion corrected line of sight, which is totally independent from GPS velocities. However, you can see this mismatch between the tracks is starting to pop out as we move down the track. And then this is an example of the uncertainties being accumulated as we calculate more and more constant offsets between them. So maybe in the future, when we have the ETAD data ready, we can potentially see if the ionospheric corrections can help us mitigate such problems. But for now, GPS is our friend. I would like to thank Chris Rollins for helping me compile this great data set of 673 GPS velocities from 24 publications, and they are converted into the ITRF 2014 fixed Eurasia reference frame. All the velocities are cleaned by an uncertainty threshold, grouped by the station names, and averaged by location. You might notice that not all of my frames have a good distribution of GPS points. To solve this problem, we have to create some dummy GPS points. And as we can see from the backdrop, which is the interpolated east velocities from the GNSS in the top panel, not all GPS velocities in Kazakh platform have 0 velocities. So we decided to sample the interpolated east velocities from the GNSS at those locations, which we need to help mosaic the interferograms. And because they are interpolated, we also sample the uncertainties from the interpolated uncertainties. So those dummy GPS would have looser control to our inside data as compared to the real GPS data. And this is what our approach in the north. In the south, where there's a clockwise rotation of the Tarim Basin relative to fixed Eurasia, we decide not to use the interpolated GPS because the GPS is too sparse there in the desert. Instead, we forward calculate the Tarim rotation for the horizontal velocities and assign an arbitrary uncertainty for the vertical component. This is our stitched line of sight velocities after mosaicing by fitting planar ramps to fit the GPS line of sight velocities. And you can see they are much more coherent now. If we decompose the line of sight just now, we can get this large-scale east and vertical velocities in ITRF 2014 reference frame in fixed Eurasia. What do we get here? If we compare this data set to the GPS velocities, we can get this difference between INSAR and the GPS at around 1.5 or 1.7 millimeter per year. If this uncertainty is equally divided between the two data sets, then we have uncertainties of the INSAR velocities below 1 millimeter per year. So what do we get here? The most obvious signal, I guess, by far you have already noticed, is this subsidence near the city of Urumqi. And this is where we have groundwater extraction to help with irrigation. And if we zoom out a little bit, can you see this broad signal of gentle uplift? And if we plot this profile perpendicular to the field, we can see this shoulder of uplift on each side. And then this is like an elastic bending, a bending beam problem, which can allow us to model for the elastic thickness. If we move here, this is the fastest melting glacier, where the glacier is thinning at a rate of meters per year. And what we are measuring is about 6 millimeter per year of uplift. So we interpret this signal as glacial isostatic adjustment. If we zoom in even more, we can see some earthquake signals. For example, here's the Jiashi earthquake, Jinghe earthquake, Hutubi earthquake. And if we want to zoom in even more, we get to the resolution of our data set, which is now at 500-meter resolution. And we get to see signals to do with the local mining activities, perhaps, and slow landslides. Now let's come back and think what we can get out of this for tectonic signals. So we can calculate the tectonic strain by using both the INSAR and the GPS, interpolated GPS north velocities, and the INSAR east velocities on the left. We treat them equally and then apply the same filter, median filter, with a 100-kilometer window. Then we can calculate the horizontal velocity gradients for each data set. Indeed, we have most of the strain of velocity gradient signals in the GPS north component, because this Tianshan is dominated by east-west striking thrust faults, which accommodate this shortening. But we can still see something in the dVe, dx, dy velocity gradients. If we combine the velocity gradient component, we can derive the second invariant, maximum shear, and the dilatation rate fields for this area. The strongest signal here is in the middle, which corresponds to the Kakura creeping section. But we don't see it much in the east-west velocities. So even though we have most of the velocity gradients in the GPS north component, I would still like to draw your attention to this very nicely localized shear, which is picked out by the dVe dy component. And if we compare that with the same component calculated from the east component of the GNSS, we can see how inadequately localized this velocity gradient is if we only have GPS velocities. And by the same reasoning, we can imply how the north velocity gradient components are also imperfectly localized at that point. Apart from that shear zone, we can also see this diagonal band of staircasing of the dVe dx gradients. And that seems to tell us about some distributed pull-apart motion here, where to the right, the east velocity will be moving to the east, and to the left, it's moving to the west. And if we really try, we can see some small velocity gradients along the Talas-Fagana fault, on which we can then plot profiles to see a bit better. So these are the profiles on the Talas-Fagana fault, and we can just about measure about 1 to 2 millimeter per year of velocity step on this fault. And here, if we plot the profiles on the Kashgar coping thrust system, curiously, can you see this length of Kashgar coping thrust system being almost dislodged and moving to the east, together with the wedge, triangular wedge on the east, also moving to the east, as if it's separate from the background in the north and south. Now, if we plot profiles perpendicular to the thrusts along the diagonal where we see the strongest velocity gradients, we can see mostly the gentle slope, almost with distributed uniform slope along the profile. But there are some localization which I picked out here with the red circles. If we draw this profile the other way around, perpendicular to the diagonal, again, we are seeing those smooth gradients and with some localization. So not all the localized share, not all the localized share are associated with active faults in the global earthquake model fault database, but they are all in the COMET Tianshan active fault database, which is coming up. So yes, stay tuned for that data set as well. So we look forward to comparing both data sets and interpret a bit more on which faults are active and what do we know about them, the slip history, etc. So in summary, what we have done here is to process 8 years of Sentinel data over a large area to produce the east and the vertical velocities at 500-meter resolution, covering 1.6 million kilometer squares of Tianshan. Here we are observing distributed east-west extension with some localized share on faults which are currently missing from the global earthquake data fault database. And we are getting a lot of information, tectonics, non-tectonics, in the vertical velocities. And their spatial pattern is helping us interpret what they are. And both the velocities here, as well as the COMET Tianshan active fault database are being fed into the global earthquake model to improve the hazard models for the next generation. That's all my talk. Thank you so much.
We have time for a few questions. I have one. That's interesting that you created the dummy GPS stations. Did you have criteria for creating such dummy stations? For example, did you make a rule that one dummy per frame, per scene, or how did you decide?
So if I scroll back, the decision was quite based on trial and error, to be honest. So our initial approach was to use as few dummy GPS as possible to pin the edges of the frames where I don't have a good distribution of the GPS velocities. But that's showing some stitching problems across the track, and we can see the track boundaries, which will be picked out as fake signals in the strain rate map. So I ended up adding more GPS, especially at the track overlaps, so as to tie them better, but giving them this large uncertainty in the interpolated GPS uncertainty map down below, so that the uncertainties are big, but then their distribution is optimized to stitch the tracks together.
Thank you.
Amazing data sets, thanks, Chi. We know from the past that in that corner of the Tarim Basin with the Pamir, there are a whole series of folds, anticlines, that are, we think are fed by thrust faults. Do you see any variation in uplift along those folds?
Yes. I didn't zoom into those. They're in a tiny corner. Yes, it's in my data set, but I didn't zoom into that yet.
Yes.
Yeah, thank you. Very nice data set. There's also an interseismic velocity model by Sabrina Metzger in the Pamir, right? I was wondering, I mean, always you ask, how's it going on, like south of this and west of this and east of this? Do you have overlap? So could you stitch together these data, even though maybe it's a bit maybe shorter, the time series of her publication? And what happens where Pamir is meeting Tianshan? I mean, there's a major divide. This is somehow at your corner.
Yeah, that's a good point. I haven't mosaic our velocities together. I think we have overlaps, but I'm not sure whether we cover all corners in that overlap. Yeah, I should check. Yes, and then as I think at the backdrop, since we're on this slide, the top panel is the east-west velocities interpolated from the GPS, and we can really see this sharp front at the Pamir front fault.
Okay, let's move on to the next talk.
Oh yes, let me introduce.
No, I can. Which is
So
me.
So the next talk is given by San Ho from Earth observation of Singapore, talking about optimally balancing INSAR observations for the damaging November 2022 magnitude 5.6 earthquake in West Java, Indonesia.
Thank you, Chi. I moved to Singapore during the pandemic, and there was a new lab building effort in Singapore. So I'm leading that lab, which is Earth Observatory Singapore Remote Sensing Lab. Because it was created during the pandemic, I thought I would give you some short introduction of the lab. So August 2021, we started with 4 founding members, as you see on the photo. This is Cheryl, my PhD student. This is Lynn, my research assistant. Now she's becoming a master's student at University of Bristol, working with Juliet Big. And that's Eleanor Einsko. Some of you are aware of her already. She studied in the UK and now a research fellow in Singapore. They're all here, flying 14, 15 hours, taking 4 hours train ride. So if you see them, say hello and talk to them. So the group is growing. As you can see, we have 6 Singaporeans, 2 Indonesian, 1 Filipino, 1 British, 1 Nicaraguan, and 1 Korean American. So what we do, we use satellite remote sensing, radar remote sensing mostly, for humanitarian assistance and disaster response. And in between the response support, we develop, improve, innovate algorithms, and sometimes AI. We tried RNN, we tried Conv LSTM, Pred RNN++, and then also we improved the automated system that would automatically discover, access, process, and produce decision support product. Impacts to date, we supported a lot of events since 2018 when I was in JPL. I was at JPL for 14 years and came to Singapore 2 years ago. But since 2018, we started collaborating with EOS and we cloned the system that was developed at JPL. And since the beginning of that collaboration, we supported 81 events to date, including the Libya flooding that we just produced and we're delivering as we speak to the World Food Program, as well as the Morocco earthquake that occurred last weekend. You can see geographically we focus on Southeast Asia, but for big events, we also support elsewhere. As you can see, the Beirut event, for example, this one here. After the explosion in Beirut, 30 minutes after the event, Sentinel-1 acquired SAR data, from which we produced a map that was used widely by NGOs and responding agencies. Featured in a lot of media, like New York Times, Washington Post, BBC News, National Geographic, and Fox News. Some turning points of our disaster response support after the Beirut event support. I got an email out of the blue from FBI saying that, oh, thank you so much for sharing your map. We were able to discover several places that are heavily damaged, which would otherwise not be discovered. So that was very nice gesture from FBI. I didn't expect this coming from explosive unit. So that's first and last email that I ever received from FBI. For some reason, they were out there checking what happened, right? After 2016 Central Italy earthquake sequence, geotechnical engineers, a group of them went out and made ground observations and confirmed that our map correlates well with what they observe as a geotechnical engineer's eyes. Back then it was as part of ARIA. I was leading the disaster response of ARIA project at JPL and Caltech. Also, Barack Obama praised our product when he was hosting Matteo Renzi, former Prime Minister of Italy, at the White House. I was invited to give presentations at the White House Conference Center 3 times following Louisiana flood, Central Italy earthquake, and Mexico City earthquake. And our map of Hurricane Dorian damage map of Bahamas was featured in the cover page of Science. I'm sharing this because I started this effort in 2009 with passion and with a group of capable people. I thought we would achieve this kind of stuff like a decade earlier. It takes more than a decade to penetrate through the resistance and convention of these responding agencies to make it really, make our maps really be used for response. So something to think about. It doesn't mean that you produce something that is potentially useful, automatically gets used. After Turkey earthquake, we produced a lot of maps covering 204,000 square kilometers. I call that 280 times the size of Singapore within 10 days, and deliver this map to the United Nations World Food Program. This is the organization who won the Nobel Peace Prize in 2020. And it's an organization that operates 30 ships, 100 planes, 5,600 trucks on the move every day. And whenever there's a big event, they need to know how many people are affected right away. So our map was quickly shared, produced and shared, and in Ankara, the Emergency Management Center in Ankara, they downloaded our map to their cell phone before they dispatched 10 teams of 50, almost 60 people to go out on the ground to make observations. Also, the World Food Program, they had a luxury to compare a lot of different products and then decided, they discovered that our product produced the number of affected people closest to the number that was generated by the Turkish government based on ground observations. They compared with all sorts of MIT product, Google, Microsoft, and Defense Innovation Unit, UC Berkeley, AI, high-resolution optical. They collected everything that are possible out there. And then they ended up writing a proposal and submitted to their own headquarters to support my lab. I didn't ask for it, but apparently they saw the value of it. Now this part 2, this is what actually I want to talk about. One of the events, there were a lot of events that we supported. One of the events was in November last year, and it's a moderate size earthquake, magnitude 5.6 in West Java, Cianjur earthquake. And that was quite alarming because it's a very fatal event. 603 people died of magnitude 5.6 earthquake, which is quite unusual. It has important implication because there are like 50 million people living in West Java. So for that event, we produced damage approximate, as you can see in the middle. But on the top right, you can see 166, almost 7,000 people were displaced. And the pressing question was, where is the safe place when they were building shelter for the displaced people? So they were talking about candidate 1, candidate 2, candidate 3 spots, and these crosshair image is showing the location of the double couple quadrant, and the question was which one is the fault plane, and which one is auxiliary. You would think with INSAR it's an easy question, but for small magnitude earthquake it's not easy. So I'll show you the interferograms, and this the star is the USGS epicenter, which is about 10 kilometers away from the actual geodetic observation made by INSAR. So this is the ALOS 2 interferogram, and one ascending, the other descending. You can see the double couple, sort of double coupleness here, this plane and this plane. And in this case, if you have two interferograms, how would you use for your own inversion to estimate the slip distribution? By the end of all this very technically dense meeting, we talked all the fancy corrections, ionospheric correction, tropospheric correction, closure phase correction. And then at the end, what you need to do is you need to decide how to weight the interferograms. I have not heard a single detailed description of how people are weighting the interferograms. I remember Shawnee was saying yesterday, we paid attention to weighting. Now, I want to pay more attention to this weighting issue. So you might think, okay, half and half, how about that? That sounds reasonable. Now the problem is, there was another interferogram because the second and third is from wide swath. And they share a very similar look angle. In that case, how would you weight those three interferograms? Is 0.3, one third, one third, one third, is that okay? Or is that not okay? If that's okay, let's say thought experiment, if the second and third became closer and closer and became identical, then what would you do? You end up weighting 1/3 and 2/3. Is that okay? Well, you just said half and a half is okay. Well, I just said half and a half is okay. Now, 1 and 2, 1/3 and 2/3 is okay. There's this fudge factor. You start finding yourself suddenly having to hand wave by the time you have to wait between different data sets. So that's what I want to address. So these are the three interferograms again, just to show you the detailed structure. This is rewrapped at what it would look like if it's X-band. Although this is L-band, you can see the structure of the deformation. And you can always estimate the spatial correlation by calculating variance and covariance matrix, but this does not solve the problem because this is data noise. But we want to talk about data signal and how important data signal is depending on, this is all about geometry. So look at data importance. This was coined by Menke, 1989. When you have model prediction, D pre, which is calculated by design matrix times your best fit model, then you can replace that model with a generalized inverse times the observation, right? You all are very familiar with this. And G and G general light inverse is what is called data resolution. And the trace of that is data importance. And that use of that work is not new. It was published in 2005 by Rowena Lohman and Mark Simons. And they compared different scheme of data reduction. In SAR, we have luxury of too many pixels, so we have to reduce the data points, and how you reduce matters. So this is about balancing pixels. And as you can see, the second one, the first two, first row, first, second, third, fourth, the results is quite different. In the second row, here, the top row shows the true solution. I think this was derived from Hectormine earthquake. But then the following rows, you can see the visually quite different. So it matters how you balance the pixels. Now then you use the data importance space subsampling. You can calculate just by plotting the data importance or trace of data resolution matrix. You can produce this data importance of each interferogram, first, second, and third interferogram, if you're looking at north-south trending fault plane. And that changes if you assume that it's a east-west trending fault plane. We go back and forth, north-south versus east-west. And then based on then important data importance calculation, we can assign a number of points to each interferogram. And it turns out for north-south trending, the balancing of the interferograms, the weight that we should give to each interferogram should be 0.66 for the first one, 0.14 for the second one, and 0.2 for the third one. Notice that the sum of the second and third is still smaller than the first one. So it's far from one-third, and one-third. And one way to maybe visually show the data, the reduction, your reduction scheme, and how you weight is assigning the proportional number of data points to reduce to. For example, if you want to use 1,000 data points for your inversion, you can distribute this way. And this is when you assume east-west trending fault plane, then you have this number of data points. So this is a work in progress. To summarize, satellite SAR observations has become one of the mainstream information at the forefront of disaster response. It took a lot of disaster response supports, communication, a lot of emails, a lot of presentations, but at last it's validated by response agencies. It's being now used, geotechnical engineers as well as Federal Bureau of Investigation. November 2022, magnitude 5.6 Cheonju earthquake really highlighted the need for rigorous balancing of multiple co-seismic interferograms, because if you come up with the wrong answer, that really affects 167,000 people, displaced people's location in a not very safe place. Again, this work is in progress, and I think data importance-based balancing has a great potential to move forward. Thank you.
Thank you for the great talk. Do we have any questions? Yes.
I would have actually two, but I start with the first one. So I'm wondering, why is it, so it's important to get the fault plane right to estimate where the aftershocks are closest then to candidate 1, 2, 3. But isn't that an information you get from aftershocks often earlier than from the second imagery? And also, I guess also in seismology is the answer, because sometimes if you have closer stations, you can get, for larger earthquakes, the directivity. Also, so is the solution maybe elsewhere? Because otherwise I would say, why we cannot tell, and then you just have to account for both cases?
That's a very good point. Seismic data is available almost immediately. It depends on the distribution of seismic stations. The accessible seismic station distribution was not ideal. If you right west of the epicenter, there's a Mount Gede, where we have our own network of seismic stations. But the station is only one side of the main shock. So aftershock, we tried relocating the aftershock seismicity, and it was not showing any. They did not align in any preferred direction. It was all cloudy, always cloudy. We even work with local collaborators in Indonesia, the government agencies. They went out in the field, made field observations. It was inclusive because it did not clearly break the surface, and there were damaged ground cracks in both directions. So one day they said this is the fault plane, and the following day they said this is the fault plane direction. So there was a lot of confusion for many days, or many months, I should say.
Thanks, very nice talk, Franco. I was wondering if you always change your data import and subsampling every time you change your geometry. Do you run the risk of somehow having a runaway, that your fault geometry goes astray because your data importer's data subsampling will somehow follow that? So
That's true. Yeah. Data importance requires your a priori knowledge of fault orientation. That's the drawback of what you proposed much earlier. Of course, then your approach and Mark's approach is prone to error, data noise. Yeah.
No, I mean, if you're searching for the geometry and then you subsample each time, you see what I mean? If you would do this in an iterative process, that you would always change the data subsampling each time that you come up with a new geometry from the Monte Carlo approach.
Yes, if you were running nonlinear inversion, trying to come up with the best fit orientation, fault geometry, then you have to resample every time. So that is true. You can't get out of it.
That's why it was the question. You could run in the risk that this would run away into some corner, you know. If you do this always, if you subsample every time that you change the geometry. I wonder if it's a stable optimization or not. That sounds like it could be that you would need to realize it somehow.
I think you just said something important, but I didn't understand. So you're suggesting something?
Well, if you have a nonlinear inversion looking at different, searching for different geometries, it seems like you need to subsample your data again and again.
Yes.
And this could be a runaway process, such that you would run into the corner with your geometry and end up with one data point, I would think. Unless you put some kind of a regularization into the system that you have a minimum amount of data points on a regularly sampled across the space.
I think there are a lot of different sampling schemes when you run inversion. But I think if you, in this case, if you remember, the focal mechanism from USGS was quite supporting the vertical, either this or that. So that sort of ruled out all the possibility. I mean, that's usually we get that information. So we have some knowledge of range of orientation, hopefully.
Great. I'm sure there will be a lot more questions, and I was too absorbed by the talk, I forgot to keep track of time. That was the alarm for 20 minutes. So let's keep all the questions to the roundtable afterwards, or maybe after the session. Now let's move on, and yes, we have the next speaker, Professor Tim Wright from the University of Leeds. I'm sure you'll know him now. So he's going to talk about from Turkey to China, tectonic strengths and velocities in the Alpine Himalayan belt from Sentinel-1, INSAR, and GNSS.
Yes, good afternoon, everybody. You'll be pleased to know I'm not going to sing. again. I'd like to present some results, really, the sort of an update on our mass processing effort. This is not something that one does alone. I've had the pleasure of working with lots of brilliant people over the years. Many of you are in the audience. Many of you are at Fringe as well. So it's been a real pleasure to have so many friends, colleagues, collaborators here in Leeds. So we're in an era of geodetic big data. This is just the GNSS sites that are processed by the Nevada Geodetic Lab. There are many, many more than that. This doesn't include all the continuous stations in China, for example. And INSAR, so Sentinel-1 has acquired a vast collection of SAR data over the whole Earth, but in particular the Earth's tectonic areas. Within the Comet LIXAR system, we've now processed more than 1.3 million interferograms. We'd like to be able to combine all of this information to get high-resolution maps of tectonic velocities and strains on a continental scale. So I guess the first question is why? It's a lot of work. I think primarily we're interested in seismic hazard models. If we look at the conventional way of calculating seismic hazard, it's primarily based on earthquakes that have happened in the past. The idea is if we can measure strain, it should be causally linked to future seismic hazard. There's a couple of correlation plots here, which doesn't prove causation, of course, between the earthquake rate and the strain rate. These are from this paper that was mentioned before by John Elliott and colleagues, but you show both in California and eastern Turkey this nice correspondence between strain rate and earthquake rate. We have a particular interest in the Alpine Himalayan belt, and really that's due to the high vulnerability to earthquakes. There's a distributed zone of intense seismicity here, and if we just plot earthquakes based on the number of people who've died with a minimum threshold of 10,000 events, about 3/4 of those events are in the Alpine Himalayan belt. Okay, so I'm going to give you a bit of a method that summarizes how we do this work, and then I'm going to focus on Tibet within that study, and then I'm going to show some highlights from work across the Alpine Himalayan belt, and then talk a little bit about the future. So, how do we do it? So this is the sort of summary of the methodology. We make the interferograms, we then invert for line of sight velocities on a frame by frame basis, and then we invert simultaneously the GNSS and the INSAR to get both the INSAR into the line of sight, into the reference frame defined by the GNSS, and also to solve for the 3D velocities and the strains at the same time. So let's start with making the interferograms. You've heard a bit about LIXAR before. We're doing that on 250 by 250 kilometer frames in general. There's a few bespoke frames that are bigger than that, particularly where they automatically define boundaries. We're right on top of faults, and that's not ideal. So there's a few but in general, they're 250 by 250 kilometers. You can read more about it in the Lezecki et al. Paper and in Milan's poster as well at this meeting. So as I said, we've got something like 1.3 million, more than 1.3 million interferograms you can download. They're all available in a fairly straightforward way to get. That's about 3 times as many as we had in Fringe 2021. So we're really in a kind of production phase of these interferograms. I should say we largely form these networks of plus or minus 5 dates from each epoch. In some cases, we've got some bespoke processing where we're adding longer interferograms, as Chi mentioned in her presentation. Here's the coherence across the Alpine Himalayan belt. You can see it's very spatially variable. We've got some beautifully coherent areas like Iran, and then we've got some areas of dense vegetation and desert with sand moving around that gives us incoherence. So it's quite spatially variable, some more straightforward areas than others to work in. If we look at Tibet in particular, I mean, these maps I think are beautiful. There's all sorts of information in these maps, but again, some spatial variation in coherence across the plateau. So what we do then is we take all those data, we invert for the line of sight velocities for each frame using LIXBAS. Yu Morishita's in the audience somewhere, or at least at the conference, so you can talk to him about that approach. We do that at 1 kilometer resolution to give us the kind of scale we're interested in for tectonics. So it's going to miss some of the finer detail, but it makes it kind of tractable to work on this kind of scale. We don't really need, for tectonics, we don't really need higher resolution than that. So overall, we've got something like 651 of these 250 by 250 kilometer frames, something like 155,000 acquisitions and 670,000 interferograms that are all going into this work. So it's a lot of data, a lot of processing that's been going on. The way we currently work on this is we remove long wavelength quadratic ramps from each frame, because we're essentially, when we adjust the reference frames, we're resolving for those, so we don't really care about the long wavelengths. Since developing this methodology, there's been, of course, lots of advances in being able to get those long wavelengths directly from the INSAR data, and I suspect in the future we'll move to be doing that. But as things stand, we use the GPS then to tie it together. So we've got a lot of data now. So we've got the colors here show the length of the network for each of those frames. So we've got at least 5 years of data everywhere across the Alpine Himalayan belt. That's the ascending, that's the descending. It's a constant battle. You finish one area and then and it's yes. So it's a constant battle, and there's a huge thanks particularly to Yasser Magsudi for managing this system so that we're continually generating these interferograms into Milan for making the codes work. So those are all the line of sight velocities. That's ascending and descending. This is plus or minus 20 millimeters per year. So we're hiding a lot of things. Some of the things that leap out, you can see some of the water subsidence signals in Iran, for example, some of the strongest signals we see there, which you see, of course, the same sign in ascending and descending. If we focus in on Tibet, you can see some features associated with tectonics. So here's the Altintag fault here. If you look at the color change across there, as others have shown, Dohua showed yesterday, you've got red-blue that switches signs showing you that it's horizontal motion across there. But this color scale is a little bit broad to see all the details we want to see. So what we really want is to actually get all these things in a sensible reference frame so we can start to understand and tie all this information together. So we do this joint inversion based on a code that we wrote that was written by Hua Wang and published in 2012 called VELMAP. And essentially what that does is we set up a triangular mesh and we solve for the velocities on each of those nodes. And we also simultaneously solve for the reference frame adjustment parameters. So it's a big inversion, essentially. And once we've got all of that, of course, you've then got information. You can go back to the original resolution of the interferograms. So if we just focus on Tibet, this is our latest velocity field model for Tibet. So we only use the horizontal GNSS in this particular inversion, but we can incorporate vertical if we've got that information and we trust it. The INSAR essentially refines and sharpens the east component. It doesn't do much to the north-south. As we know, we don't have much sensitivity there. And you can see the kind of broadly the difference in texture between that east-west velocity and the north-south velocity in those, and that's the sharpness is coming from the INSAR. The vertical component is also coming from the INSAR in this case. We put a constraint that the average is 0, and those are the smooth verticals that we need in order to be able to tie everything together and for the long wavelengths to make sense. So those are our mosaics, ascending and descending velocities. Obviously a different sign, so Tibet is, there's a lot of east-west motion as well as the north-south convergence, and that gives you an opposite sign in the ascending and the descending. Once you've got that reference, so these are referenced back at the full resolution that we put in, so back at that 1 kilometer resolution, and that's the prediction from the VELMAP model. So the nice thing about that VELMAP triangular mesh model is it gets rid of some of these noise features that people have been talking about. So a lot of those can't contribute to the horizontal velocities. It gets rid of any short wavelength things. So most things in here should be tectonics in that model. And it fits the data pretty well. There's a lot of short wavelength features in the residuals, but probably these are largely non-tectonic. From that, you also get the strain rate fields derived from the velocity field model. So those are the three components of the horizontal strain rate tensor. In A, B, and C there, and in D, we've got the dilatation, the maximum shear strain, and the second invariant, which is a measure of the magnitude. And I'll talk about what these mean in a bit later. Just an obvious question is how much impact does the INSAR have on this inversion? So what you can see here is the eastward velocity and the shear strain rate with and without the INSAR. And you can see what it's doing is it's really focusing things in on some of the big faults here. So it's making the strain rate along, for example, the Altentarg fault much more consistent along strike, and it's really just sharpening up that entire strain rate field really nicely. So we're also interested in, rather than looking at ascending and descending geometries, also interested in referencing that into looking at the east-west and the vertical velocities, essentially. So we do this sort of standard pixel-wise inversion here. We're assuming the north-south velocities that we get from that mesh inversion are correct, and we're combining all that, and that gives us these INSAR resolution east-west velocity fields and vertical velocity field. So again, a really beautiful data set. You can see very nicely, even just looking at this without thinking about the strains, you can see these quite strong changes in velocity associated with some of the big faults, like the Altentarg fault, the Kunlun fault, and others. The vertical field, as Chi mentioned, is a bit more variable. There's lots of contributions in the vertical. There's probably also some phase bias, which largely maps into the vertical. You can see some short wavelength features associated with resource extraction, but there are some long wavelength features there that I think are genuinely tectonic. But there's some work to be done, I think, to disentangle the noise contributions, the hydrological loading contributions from the genuine tectonic contributions here. But there's some tantalizing features in that vertical field that I'm not going to say much more about. Let's focus on the strain rates. So what are the key features we're seeing in the velocity of Tibet? I think the big obvious one is we're seeing this focused strain on a bunch of major faults. So really the big faults are the ones where we're seeing the concentrated strain. We're also seeing some long-lived post-seismic from the Mani earthquake, the Kunlun earthquake in particular, potentially also around Yuchan here from 2008. Even though that wasn't a strike-slip fault, there seems to be a concentration of strain in that region. We've got regions of low strain. Again, these were known about beforehand. But within the plateau itself, the central, south-central plateau, it seems to be fairly distributed, the strain. If we look at the dilatation field or the dilation field, I've asked lots of people whether there's a difference between dilatation and dilation, and nobody seems any the wiser. If anyone actually knows, then please tell me. I apologize if I've got it wrong. I've used both on this slide just to cover all bases. But the south-central, so central Tibet is basically extending sort of perpendicular to the collision. And then we've got these areas of contraction, obviously around the Himalayas, also in the northeast region and in the Tian Shan, as Chi showed as well. If we look at how to model that, and you can read a lot more about this in this preprint paper and also in a companion paper with work done led by Jin Fang in the audience, who's done a lot of this work on modeling. If you want to try and model this with a dynamic model, you need a combination of continuous deformation, but also some focused deformation around the faults. And those faults seem to make quite a long wavelength difference to the deformation field. They're not just influencing the area near the faults, which was, I guess, my prejudice before we did those calculations. They have a long wavelength influence. So I'm just going to end by sort of showing a few. How long have I got left, Chi?
1 minute. Okay,
3 minutes. I was 5 minutes late when we started. Thanks
sure.
So, okay.
Fair enough.
Okay. Right, so I'm just going to quickly just highlight a few results. So you'll hear more about some of these later in the next talk in this area. But this is work we've done in Turkey. This is published. I'll flick through this. But the strain rates here are very similar to the most recent seismic hazard model, which was derived independently. And if we just look in the area of the earthquake, as others have shown, there was strain accumulation in that area that you see very clearly also in the GNSS data. I also want to highlight work by Andrew Watson and Jessica Payne, who've been doing these, looking and analysing these velocities across all of Iran, and there are posters on this in the poster hall, so I encourage you to go and see those posters as well. Similarly, Jin Fang has done a really beautiful detailed study in southeastern Tibet, and they're looking at really refining those networks, doing a lot more work that you can do when you're trying to do the whole plateau. Number of things you see here, most notably this very high strain here. This is an area of fault creep on the Zhenshuhe fault. But also, one thing he's done, and you can look at his poster, is compared it to a block model in this region with the block boundaries defined before we had the INSAR. And you can see a number of areas of misfit. For example, here, that's a block boundary. And as soon as you put a boundary in, you get strain on that boundary, but there's no strain in that location in the real data. So go and have a chat at his poster, really interesting results, I think. We heard also various results already in this meeting from Qi, we heard earlier, Dohua yesterday on the Altintag fault, and Lin Shen has a paper in review, which I'm sure she would share if you have detail. The interesting thing in Lin's paper, as she's not presented at this meeting, is there's quite a variation in the degree of localization of strain on the Altintag fault itself compared to strain in a broader shear zone, and that seems to vary along the fault. So just a quick outlook. I think this is a really exciting time for tectonic INSAR with the Sentinels and the future generations of those missions, the Roselle and the Harmony missions, and NISAR coming up as well. So it's a really exciting time. So just to conclude, we can combine lots of data, map tectonic strain now over really large areas, and it's really thanks to the large open archive from Sentinel-1 that's made this work possible. We get good results for the automatic processing, and when people put the real effort into refining that in smaller areas, we get even better results. And they're telling us some really interesting things about the geodynamics. So I shall leave it there. Thank you.
Great. Thank you very much. Are there any burning questions which we can ask now? Otherwise, I think Tim gave us like a very nice outlook and overview, which might be a very good introduction to the roundtable discussion. So any questions specific to Tim's talk now? Oh, yes, we have one.
Just a bit neat speaking. I was wondering, you guys are fitting heavily to the GPS, but then you said, I guess, so by that time, the GPS and INSAR are aligned. I would have expected that everything is the reference frame already. So why in the inversion, you still, you said that you guys are inverting for the reference frame rotation still? Maybe I'm
quite, so the microphone is quite boomy, isn't it? So we're inverting for the, why are we inverting for the?
Reference frame.
Because, well, I should be clear actually, we're only adjusting the reference of the INSAR to essentially it ties it to the GNSS. But if you do it we do that as one big inversion rather than frame by frame. If you do it frame by frame, you don't necessarily get consistencies between the frames, and also there are frames with very few GNSS in there. So if you do it all together, then you get the benefit of tying, a frame in the middle that has no GNSS in it is still tied into the reference frame. So we do it all together for that reason. Does that answer the question?
Thank you. Yeah. My misunderstanding. I thought you were double doing the.
No, we just do it once. So we flatten everything, and then we invert in that joint inversion for velocities and reference frame.
Okay, thanks.
Great. Okay.
Thank you.
Thank you. So now let's welcome our last speaker, Chris Rollins from GNS Science, talking about strain rates in the Anatolian Caucasus region from Sentinel-1 INSAR and the GNSS, and the quantitative comparison with earthquake catalogs.
good. Hi, everyone. Thanks for staying to the end of the session. This is work I've been doing too slowly over the past 4 years and really need to write up. From 2019 to 2021, I was a postdoc at Leeds, and this is the work that I started there and kind of am continuing when I can. And it's focused on the Anatolia to Caucasus region, just shown on Google Maps here. Most of you might be familiar with this scheme by now, especially from the session this morning, but the tectonics of Anatolia and the Caucasus are kind of driven by the Arabian plate impinging upon the Eurasian plate. Let me just do this. The Eurasian plate from the south, and Anatolia is being squeezed out to the west, sort of like if you're trying to squeeze a seed out of a watermelon with your thumb. Arabia is your thumb, Anatolia is the seed, at least that's one model of it. And then the Caucasus are also being built by this collision further to the east. Anatolia is also being pulled towards Hellenic subduction, so there's extension going on internally. But as you'll see, a lot of the motion we can see is this big wholesale block rotation. And then the Caucasus mountain building, it builds some very high mountains, including Elbrus, which is about 18,000 feet, is the highest mountain in Europe. And a lot of Anatolia's wholesale motion with respect to Eurasia and Arabia takes place along two strike-slip faults that are conjugate, the North Anatolian Fault and the East Anatolian Fault. North Anatolian Fault being right lateral, East Anatolian Fault being left lateral. The East Anatolian Fault no longer needs an introduction for the worst possible reason. It's the earthquake, it's the fault that ruptured in the 7.8 earthquake earlier in February this year. And also in an earthquake of magnitude 6.8 in 2020. And then the North Anatolian Fault has had a earthquake sequence of its own that's caused a lot of fatalities as well over the past 120 years. It was kind of kicked off by a 7.8 earthquake, like the initial one in February. In 1939, the city called it Erzincan, and that started here and I believe propagated to the west in a sort of tragic parallel to the 2023 earthquake. A blizzard dropped in 2 days after the earthquake and basically hampered rescue efforts the same way that happened after the February earthquakes. Then there was a westward unzipping of the North Anatolian Fault throughout the remainder of the 20th century, culminating in the devastating Izmit earthquake, 7.6 in 1999. And there's an unruptured gap south of Istanbul along the Marmara segment that's received a lot of attention and a lot of anxiety, understandably, since this has all been going on, but especially recently. And so we have these devastating earthquakes. Istanbul is threatened by them, possibly going into the future. Turkey is, it's maybe doing the best it can, but it's got infrastructure problems everywhere. And so, one thing that we can try to do to help is try to figure out what's going on year by year, kilometer scale in terms of the tectonics and the tectonic loading, and can we see that from space? And then going from that into what might that imply for earthquake hazard. Can you guys hear me okay? Am I too far? Okay, great. All right, so here's what we can see from space, kilometer by kilometer, or I think this is multi-looked, but this is from LIXBAS, which Tim explained. This is the COMET's INSAR processing service, and these are velocity maps. And so each of these is a frame, so there's a number corresponding to the frame. We have 83 frames total that we used. This is a pastiche of a few different processing efforts that Yasser and Milan have done over the past few years, and I just picked the least noisy looking one in each frame, kind of in a not particularly sound way, but just based on eye for this purpose. But essentially, you see a lot going on, and then this kind of gets to the question Haresh asked Tim, which is, you don't see a lot of like wholesale Anatolia motion, and the reason is that all of these frames, all these velocities are referenced to a 0 point in somewhere in each of these frames. So frame 14 might be referenced to a 0 point right there. And so it doesn't know that it's in Anatolia, it just knows how fast stuff is going with respect to that point. Similarly, frame 27 doesn't know it's in Georgia, it just knows how fast stuff is moving with respect to whatever reference point. So we need to unzero these frames by tying them to a GNSS velocity field that knows about Eurasia's motion relative to Anatolia and vice versa. You can see some features that do pop up even without sort of de-zeroing. This bullet hole here is the Konya Basin, which is a giant agricultural or hydrological center. And you think you might be able to see some things coming down in the Caucasus over here, and some signal along the North Anatolian Fault, which we'll see much better in a few slides. And then this is the descending track, and you can maybe see some signal along the East Anatolian Fault and over here. But we need to, again, unzero these. So to do that, we compile a big, we put together a big compilation of GNSS velocities throughout this region. And these are basically compiled from me trawling Google Scholar and various other things in the past 3 years, and just finding the global strain rate model compilation, which is Kramer et al. 2014, and then everything that was published after them or that they didn't use for some reason and deserves use. There's a few different criteria for how I select these. They gotta be published in a Eurasia fixed frame that they explain and that you can Euler pull rotate back into a Eurasia fixed frame of other studies, stuff like that. It's gotta be internally consistent. But yeah, so these are all of these studies that I use. This is a big new compilation from this past year that was super useful. This is another one that I just added a couple days ago from the same journal article, and then this one also. There's a few studies in here. I think there's 7 that I added in the last like 3 days. So when you apply some, okay, so the first thing that we do, and she kind of mentioned this, we up-reference the locations of these to the most precise locations by basically going through common station names, and I won't go into that, but basically, if some study publishes ARC1 station, but only rounds the latitude and longitude to the 2 decimal places, but another study didn't round it and has it at 6 decimal places, then we we identify the similar name and move the 2 decimal place station to the 6 decimal place location. And then, so we do that. That matters more in China for cheese work. But we also do it here. And then we do some culling based on the total horizontal and vertical uncertainties. And so we're just trying to remove really bad velocities in a rigorous way. It's not always rigorous because we do some outlier removal by eye. And there's nothing sacred about how that's done, but I think we got most of the outliers that are really obvious. And so you can see that we start to thin it. This is actually fairly generous as far as criteria, because what we do next is average them and propagate the uncertainties fully into a combined uncertainty on each of these velocities. So it's a weighted mean based on the individual uncertainties of the individual velocities going into each station, and then we also do propagate the uncertainty formally. So we get this sort of nice even GPS velocity field across the Anatolia-Caucasus region. And then you can see the wholesale rotation of Anatolia counterclockwise relative to Eurasia. This is fixed to Eurasia, or relative to Eurasia in the ITRF Eurasia frame, like the one that she showed. And yeah, then you can see the slowdown across the Caucasus, and that's, so Tim explained VelMap somewhat, but basically it's our in-house strain and velocity mapping program, and also solves for the other stuff that may not have been removed correctly in processing, such as orbital and atmospheric errors, and biquadratic and bilinear ramps if you want. We did put those into the model, just in case they remain in Lix-Bass velocities. So, and then this is our model mesh, these gray triangles. And so what VelMap does is solve for the velocity at each of these mesh corners, and then there's a strain interpolation step that happens after. Okay, so the next step is the part that's a little bit new. I should have made a slide about it, but I was too busy rerunning models at the last minute. But actually, Sung Ho helped introduce this pretty well, which is in terms of model resolution and data resolution, like you don't have very much resolution coming from the GNSS in, for example, here. You don't have any stations. You have a lot of resolution over here. Now, one of the things that VelMap uses is traditional second-order Tikhonov regularization, where the roughness of this triangle mesh motion solution is penalized. So it's not too rough, it's not too disjointed. Now, that's generally a good idea, but if you picture a creeping fault, it's going to have a sharp offset with infinite strain. So it's going to over-smooth that kind of feature. And that's an extreme example, but there's always kind of a battle between you don't want to over-smooth legit signals coming from faults, but you also don't want giant blobs where you have no data just because the model is floating between different possible realizations and has no preference for one or another. So what I did for this is you run a bunch of jackknife, which is related to Bootstrap. You run a bunch of jackknife samples of the GPS velocities, fit a VelMap model to each of them, and then take the median model at the end. In this case, I used 150 different random samples of the GPS sites, anywhere from only 10 velocities, or that was the lower limit that I imposed, to all of them, and it's just a random number. And you keep the sites the same, you keep all the velocities if you pick a site to remain in. And so when you do that and then take the median model, it helps beat down the sort of blobby effects that you get from undersmoothing away from faults, while also not smoothing too much along faults where you have an actual gradient in velocity. And so yeah, you get this output model, which this is colored by eastward velocity, reference to Eurasia, so you can see the westward motion of Anatolia coming up pretty well. And also a little bit of eastward motion in the Caucasus, which is consistent with the GPS and sort of guided by it. And then this is the north-south, and you can see north going to southward, so that's, and then the slowdown across the Caucasus. And then this is the up, which it's a continual battle to keep this not too rough. And this is, it's sort of an art, if I were to call it that, to, you know, do this in terms of smoothing versus bootstrapping and how many bootstrapping sample or jackknife samples you want to run versus your mesh size versus your GPS and INSAR uncertainty. This is what happens, by the way, if you don't put dummy sites that she was talking about. I tried not to, and I think I'm going to have to put one there because this corner of, I think it's Dagestan, is just, it just always goes up at 12 millimeters per year for no reason. But the rest of this looks fairly consistent with the GPS verticals, which are these colored circles. And then these are the original INSAR velocities. These are the unzeroed INSAR velocities in the descending track, and so you can start to see the gradient across the EAF and the North Anatolian fault come up pretty well here, and then also some of these signals across the Caucasus faults possibly, and that one. And then these are the ascending track original velocities, and these are the unzeroed ascending track. It doesn't look as convincing. I think this frame we need to work on, and I just realized that this morning. But there's a lot of good stuff coming out of it. You can see this gradient across the greater Caucasus fold and thrust belt, which we'll see in a second. Actually, we'll just see it right now. This is the strain, the second invariant of the strain rate that you get out of this model. And so this is what we care about because it's related to earthquakes, because earthquakes release strain, they don't release velocity. So this map has a lot of interesting features. The North Anatolian fault is the big player in strain accumulation, as kind of was already known. We see some sort of spotty stuff coming down the EAF, and it is non-zero in the area where the 7.8 earthquake occurred. Let me just see how I'm doing, okay. And then the greater Caucasus fold and thrust belt shows up pretty well. And we think we see some other features in Western Turkey that may be phase bias, but it may be legit tectonics. And I'll just speed up. So what we want to do is relate this to earthquake occurrence in a quantitative way. So what we do is compile a combined earthquake catalog, sort of the way we do with the GPS, but just with earthquake locations, trying to pick the best for each given earthquake based on what different catalogs are good at and specialize in. And so we put together this regional catalog for Anatolia and the Caucasus. It goes back to the year, I think it goes back to 342 BC, thanks to Marco Bonhoeff's catalog, along the NAF, which we used. You can see to first order the locations of earthquakes and strain agree pretty well. Of course, the NAF dominates that correlation. So in some places, you get earthquakes off in the middle of nowhere in terms of strain. The Dead Sea Fault doesn't come up as well because, well, the INSAR is less sensitive to it. I know Andy Hooper and his group have been doing a lot of stuff that might help with that in the future with north-south. And then you can see the Greater Caucasus Fold and Thrust Belt. This is probably a very incomplete catalog, I've realized over here. And this is this is magnitude 5.5 and greater anyway. But we can make this more quantitative by going to turning strain rate into moment deficit buildup rate by just, Dave was talking about this earlier, but you just assume that the strain is continuous down to an effective locking depth, and you multiply, you integrate over this volume, multiply by the shear modulus, and you get to moment deficit accumulation, which can be compared to moment release in earthquakes. This is our locking depth grid. This is preliminary, but basically this is Iqbal Hussein's locking depths across the NAF. We assume 15 most elsewhere because I haven't looked at it yet. 5 on the northern or the northeastern part of the EAF that's based on Canton Blettery's work, and then 10 for the extensional part of Turkey, that's just a guess, totally just a guess. But yeah, so then you can convert strain rate to moment deficit buildup rate, and then you can start to look at individual faults and whether the moment release in the catalog compares to how it compares to the moment buildup we see from the geodesy. So if we isolate a plus or minus 60 kilometer sort of sausage around the NAF and look at earthquakes versus moment deficit buildup rate, that's the deficit buildup rate per year, and that's the moment release rate in earthquakes since 1900. So it actually is almost in moment balance since 1900. Now we know that the last 100 years along the NAF are not, it's an earthquake storm or earthquake cycle, and there's probably a silence that happens in between each of these. There might have been, a 250-year gap since the last giant earthquake in 1668. So we want to integrate a little bit further back in time to get a more balanced picture. So if we go back to 1450, which is when the Ottoman Empire was kind of consolidating and probably record keeping and record communication into the future was improving throughout Turkey, we can look at earthquakes, giant earthquakes since 1450. It's actually behind in moment deficit buildup rate. There's a few reasons for that I probably won't have time to go into the details of. But if we look at the EAF, if we go back to 1900, it is way ahead of moment deficit buildup rate. It's 2.5 times it. And if we go back to 1450, it's actually in moment balance. So again, this catalog is probably very incomplete. This moment deficit and strain picture there's a lot of work to be done to refine this with some of the methods that Chi and folks like Dehua were showing, which helps localize this a lot more. But it's just an interesting, I think this is interesting that it's almost kind of in moment balance in the last 500 years. Tragically, it required the 2 earthquakes this year to have that be the case. And we'll go forward assessing the robustness of that more. These are kind of some of the things that might fall into it. And I've gone way over time, right? Well, yeah, I mean, so some of the things that complicate this comparison are, we're still aliasing some creep as seismic strain buildup, but non-tectonic deformation, phase bias, hydrological stuff. And so we might be overestimating the moment buildup rate. And then the earthquake catalog is probably not complete, especially pre-1900, although many teams are trying to make it better. And there's a couple of regional catalogs that I need to digest into this that hopefully will improve in that. And yeah, I'll just leave it with that.
Great. Okay, shall we have one question, if there's any?
Thanks, Chris. Great work. I just wanted to ask, I have loads of questions, but the one I want to ask you about is the two Dusche earthquakes, the one in '99 and the one last year. If you were to do a calculation of the strain buildup since the last earthquake to last year, does it equate to the moment release and the earthquake last 2022? Would it?
That's a really good thing to check. I'm not sure. This catalog, I think, only goes to 2018 because it uses what was the most recent ISC GEM catalog to do a lot of the since 2012. But that would be a good. That definitely would be a good thing to investigate. That'd probably be a good kind of lab-like test case for this kind of stuff. So thanks.
Do you find a correlation between the moment rate and the amount of smoothing that you put into the bell map?
I think it's a slightly inverse correlation. Like you over smooth. So the bootstrapping or the jackknife with under smoothing and then take the median was an attempt to leave in whatever seemed legit, especially from the GPS. So for example, if you run a GPS, I didn't show this, but if you run a GNSS only strain model, there's so much GNSS along the NAF that it almost looks the same. So that's possibly an okay result, but yeah, probably the most appropriate thing is to use methods like cheese or dehuas going forward so that are smoothingless and not model-less or more so. But the most appropriate thing for me to do is to write this up. It's been too long.
Okay, then we conclude this session, but I don't want to create a sense of ending and let you go because we have round table, right? Okay. So how do we do the round table? We are oh, okay. Why don't you, all the chairs come out? Oh, is there a break?
I think that's a typo.
Huh?
Yeah, I think that's a typo. In the other room, they just continued straight to the round table.
Yeah, it's easier to just have round table and break. Well, why don't we have individual break? John, you can go to restroom.
Yes, I think so. I guess so. Like, there are 8 questions. Yeah, cool. Thanks so much. Amazing.